a convergent sequence of real numbers is bounded. Okay. And intuitively, what's the best way to think about this is to compare the picture of a convergence sequence with a picture of a open set on the real number line, right? It's supposed to go fast, but I could just quickly do this. No, once I make the picture, we'll look at that. And then, so somebody remind me to bring that in. Now, this is not in the if-then formulation. We could also write it like this. If you have a convergence sequence, then it will be bounded. Okay, something like that. All right, and then here we go. Convergence sequence. How do we represent it mathematically? Anybody remember? Okay, so we do n is greater than or equal to uppercase N. So all terms n that come after the term in the sequence that has an index number uppercase N, these are natural numbers, terms with the index n that come after the term with the uppercase N, which indicates that all the terms after that will be inside, will be clustering around the limit. So we write this. If this is true, then, and if this is true, what was this? An minus a, all terms an that are within epsilon distance of the limit L, a, this is the limit. And epsilon, of course, is a positive number with any value. This needs to be true for any value, positive value of epsilon. And then we write what? This, if this is true, this thing in square brackets is true. If what I just wrote is true about a sequence, then it implies what according to the theorem? First of all, this says an is, what kind of sequence is it? What is this telling you that an is? So an is a sequence, and this thing is telling us that an is, okay, I'm doing what I did last time. We'll run out of time. So I'm just gonna, yes, everybody gets this? This is a way to say a sequence is convergent. Okay. And then if you have a convergent sequence, the theorem is saying that this sequence is bounded from both from the right and the left. And so we put this here. M is the upper bound. M is a number. So there is a number M larger than the infinitely many terms of the sequence. Upper bound in this case would be positive, and then if you expand it, you get the, whatever you calculate, put a minus sign on it, and that will be the lower bound. Okay, and we'll do that. So in other words, this is right. We did this last time. Right. So this is saying that our sequence of real numbers is bounded by a number m from the right and bounded by minus m from the left. Okay. And in other words, our sequence an is within this closed interval. Okay, all right. So we're doing a direct proof. So proof direct, and then all of this is assumed to be true, and this is what we want to prove. So in other words, this we are given, and this we have to prove. All right, so so this is what I wrote last time. Suppose, and this is what the book says, suppose that lim of an, you don't have to do the n goes to infinity here, equals a, and let epsilon equal be defined as the number 1. Okay. Can anybody tell me quickly why I could write this? Because what am I doing here? The first line, how did I get the first line? I got the first line from the theorem. You guys were paying attention last time. So, Chris? Yes. And we have assumed that the sequence in this sentence is convergent. If the sequence is when a sequence is convergent, you can say two things about a sequence. You can say it's convergent, which means it has a limit. When I say an has a limit a, I'm saying that this is a sequence that converges on this limit a. So saying a sequence has a limit means I'm saying it's a convergent sequence. Convergence and the word term limit are the same thing. Okay, so for some weird reason, the proof starts with using the because this is the definition that I actually describes convergence very well. The epsilon, the limit doesn't do that. Okay, all right. Next, what values can we choose for 1? Do you guys remember? Every value of epsilon better work. All terms after the threshold term better be within epsilon distance of the limit. In other words, epsilon better be, epsilon can be any value and it should still work. That's the whole thing here. Okay, all right. And then if this is true, then, and now he goes on to say, then there exists, in other words, if the sequence is convergent or if the sequence has a limit, and we choose epsilon value to be 1, then there exists a natural number. What is that natural number? And where are we getting that number? From the antecedent, right? Remember, this is the antecedent. What's the other term for antecedent? Hypotheses. This is what we assume to be true, and then we use this information to show that this is true. And this is what? The conclusion or the consequent. The consequent is the other word. This is the consequence of assuming this. This says our convergence sequence is bounded by a number m, a real number m. Okay, all right, let's keep going here. So what should I put here? What should exist in the indices? What special number are we looking for? A real number or a natural number? What is this guy here? Is that a real number or a natural number? Natural number. All right, so I'm going to put n here. This exists. This is a natural number. And actually, this, I actually wrote the number already. Natural number n, and such that, and now I'm going to write this out here such that all terms an are within epsilon distance of the limit a for all. So what's missing? What do I have to write to make this work? So then there exists a natural number n such that all the terms of the sequence, did I miss anything here? What condition do I put here? Grace? That's the hint. And what does that do? That says that this relationship is true only for the terms that are clustering around the limit, not the beginning terms of the sequence. Okay, so this is a key thing that you need. Okay, and after this, is there anything else that we can expand? Because we have assumed the antecedent to be true, this is the arsenal of democracy. This is the arsenal from our assumptions that we can use to prove this. This is where we stopped last time. Okay, and now the next line is we're going to apply. So remember, we're going to bring in a set. We're going to apply the supremum idea, and we're going to apply the triangle inequality theorem right now. Triangle inequality theorem was this: a plus b in absolute value signs is or equal to less than. So if you add the two numbers and take the absolute values or put it in the absolute value function, the result will always be smaller than or equal to if you applied the absolute value function individually first to the a and b and then add it. And when we did that last time on Wednesday, so I'm not going to repeat. At this point, let's draw the picture. What picture do we have? We have the picture from the antecedent. We have expanded and looked at see, so I think I'm going to erase this, just erase this. We took this phrase, a convergent sequence of real numbers. And what does it, and how do you say that in math? Like that. These three lines are the same as saying convergent sequence of real numbers. And then here is and I'm going to keep this guy here. So an is less than or equal to m, because this is what we need to prove. Okay, so we draw the picture here. All right, so what do I stick here? A1, first term of the sequence. A2, second term of the sequence. A3, third term of the sequence. If I keep going towards the right forever, then this infinite sequence does not have a limit. It does not converge on a limit. So what needs to happen now? We need to get to a place. Let's say our limit is sitting here, and our epsilon is 1. So we have a plus epsilon and a minus epsilon. We need, let's throw this guy in. How many more elements do we need? How many more terms do we need before we get to the n term? It could be million. You might go through 1,000,000 terms before you run into that. So let's say our last term outside was A4. Our next one that will end up being one of the clustering terms, let's put it right here. So what is the index number here? N, and this giant N equals, by the way, the picture represents it. It should be what? What number should it be? 5, very good, okay. And I'm going to make this a little longer here. Hey, here we go. And why did I put, and after this, all the other terms that come after a sub 5 will always fall around the limit a, right? So how many are there? Infinite, very good, thank you. Okay, this is the situation we have right now. This is what we got from the antecedent. This is all the information we have in order to get to this. Now, let's just do for comparison. This looks very much like a open set, let's say 1 and 2. Does this open set have does it have a upper bound? Yes, very good. This open set has an upper bound, and it is 2, and it's also the least upper bound or the supremum. Does it have more upper bounds? Yes. Everything outside of the red line is an upper bound, and there are infinitely many numbers between 1 and 2. So this is an upper bound. What number should M be? We could call it 10. We could say 2.3. Any number bigger than 2. 2 is also an upper bound. This is definitely above. We could say that this set A has an upper bound M. And what we're trying to ask is, does this sequence of terms, does it have an M like that or not? And it turns out the resemblance is right there. Obviously, it does have it. And what we have to do is calculate it. Okay, all right. So erase this, we move on. And now we're going to apply the triangle inequality in order to get to our home run. So here we go. If we apply, and this is where we stopped last time, if we apply the triangle inequality with n is greater than or equal to n, we obtain this thing. Okay, so question number 1. That looks terrible. We got this, and we got this from the antecedent. Did we get this from the antecedent too or not? This is a true statement that I've just written. And I'm going to apply the triangle inequality to this thing here so that I can go from here. What does this is supposed to look like what by the end? We have to get to this, right? The question I'm asking is, who gave me the right to put that down? Is this true? Where did I find it? Did I go to the conclusion part of the theorem? I might have, I did perhaps, but I only picked the part that is already assumed to be true. We don't know at this point. We're going to show that a convergent sequence has an upper bound. But at this point, we have assumed that we have a convergence sequence. And so we can write that. This is coming straight out of that we have a convergence sequence. And all we have done is, so this is coming, we have this, right? AN defined to be a convergence sequence. And all we have done is put absolute value signs around it. So first step, oh, okay. In other words, we are still where? We're still on the antecedent, is what I'm saying. And we're gonna take the antecedent and run with it, run all the way to this formulation. So we took this. Does it look like that? No. But if I put absolute value signs around it, does it change its value? No. Therefore, we're good. All right, here we go. So everybody good? And what's the next step? We have to apply the triangle inequality. And oh yeah, this thing here. What does this mean? This condition that we're applying on this thing that we took from the antecedent says that the only terms of the sequence that we are really concerned and bothered with are the terms that are found where in this picture? The ones in the open interval. In other words, we will be able to generate, calculate a upper bound M by just messing around with the clustering terms. That's why this condition is there. Because we don't really care that these are not really useful. This will generate that because, okay, just like that picture I drew about the open interval, all you care about is that set. And then an upper bound is to the right of it. Okay, all right. So I'm going to go, unfortunately, I should have a second, and then I have to change the camera position, but we're not doing that. So I'm going to delete this line here. Oh, also I kept forgetting. How big should the epsilon be? We have assumed it to be 1, right? So I'm changing that. This is 1. Would it work for half? We would just have to change the number n to a bigger number, right? So let's say an was here, an. Yeah, so anyway, I've gone over that before, so I'm not going to go over that. Again, we don't have time. All right, equals 5. All right. So I have this. What should I do to this thing here? And I'm like, okay, I need something like that. I need a sum. So what I need to do is do something to that thing that is true without changing its value. So applying the triangle inequality to this thing, we get we haven't actually applied the we will. So I'm just going to say we will apply. We haven't. You guys understand that? Because in the textbook it's different, and I did it to lay it out. So I'm going to say an. What should I do to this thing here? Any guesses? I need a b, right? What should be the b? I need to add something and subtract something from this so that this is still equal to what we have on the left-hand side. We need a b, right? All we have is the a. This is a number, a real number. This is a real number. Here we have all the clustering terms. This is the nth term of the sequence. And this, we look at this and we go, maybe all we have to do is add and subtract the I need the minus first, yes. Add and subtract the limit. Is the right-hand side equal to the left-hand side? Yep, there has been no change. Ryan, is there another way to think about this? How did I come about doing this? Because we do have a limit. That's a number that we can add and subtract, right, to this. Yeah, and it doesn't change anything. If I had just subtracted the limit from the terms an, then I would have changed it. This equality still holds. Okay, all right. Once you've done that, this is, now we are ready to apply the triangle inequality. So what is going to be our A? Our B? Our B will end up being this, and our A is going to end up being this. Vincent, what do you think? So in other words, it's going to be this situation here. Yes, good. Okay, so at this moment, I apply. Have I applied the triangle inequality yet? No. All I did was add and subtract the limit from the terms an, which seems natural. Because you're struggling with this, this is what you'll end up doing. And then you go applying it. So now we're applying. This is applying. What's the step here? This thing is going to look like this sum is going to be less than or equal to this sum is going to be less than or equal to so okay, is anybody confused about this? This is our A gets its own little thing. This is our B gets its own, right? So we are now thinking of this as a term, and this is as a, we're thinking of this difference as a term A in the definition of, this is the definition of triangle inequality that I wrote out last time. This is the definition of triangle inequality. And we look at this and we go, okay, how do I come up with this thing? This whole thing resembles this thing in the box here. All the non-science STEM people, be aware. Okay, now what? Is this a number? How many people think that this thing is a number? Yes, A is the limit. It's a real number. Is it a term of the sequence? Maybe, maybe not necessarily. Is this a number? Why is this a number? Because the first line of the proof gave epsilon a value equals to 1. So this, in fact, this number is less than 1. And this is whatever, it could be any big number. I mean, this is actually the value of the limit. So in other words, let's say if this is 4.3, our first number, our second number is 15 mil. Let's just make it simpler than that. 5.7. This is 6.8. This is 3.1, smaller number than before. This is the sequence. The fourth number is smaller than the first three numbers. And then we get in here, and now there'll be infinitely many numbers within epsilon distance of this guy here. Okay, so A could be maybe, let's call it 5. No, 15. If I add 1 to 15, I'm going to go right here, 16. 16 is our M.
I don't understand.
Oh, because the sequence, this might not be an increasing sequence. It could be a sequence.
Okay, so
Yeah, it's increasing and then it starts to decrease and then it increases again. Huh? Why not? Yeah. Okay. All right. Let's. But in fact, you're right. It's an increasing because otherwise this would be here. It wouldn't work. So let's do 8, and then our limit is 15, and then all the numbers will be slightly bigger than 8, but always smaller than any number that goes there. Very good. Okay. All right. Thank you. Okay. So our next step is this thing. So what do we have? We have an. This guy is less than or equal to. So I'm rewriting this. Okay. So this is already a number. We need a value for that. So therefore, all terms, or at this point, we can also say these sequence, including these early terms, this sequence is, I'm going to replace this with what? 1. This is already a number, so I rewrite it down here. Can I put equal to sign here now? Because of this, so it becomes this. Therefore, okay, and so, and what do we have here? Okay. Oh shit, this is forever. Okay. So where do we make it in our picture? So this is A plus 1. We have all the terms of the sequence are less than the limit plus 1. The limit is here. And if you add 1 to it, it's going to end up right here. Does that make sense? Is this number bigger than any term of the sequence? Yes, right? It's to the right of all the terms of the sequence. Therefore, this is our M. Okay, so we can't just say that now. We can't say, yeah, this is our upper bound, but now what we have to do is, I have a picture. So we're using this picture, and the picture tells us this is the upper bound because this number here is bigger than any term of the sequence. It comes to the right of it. When you read the book, you don't have this picture to locate that. So what you do is, I'll delete this. You say that my M, the upper bound that I'm looking for, equals the supremum, the largest upper bound, the least upper bound, the leftmost upper bound of this set here. And what's the set? We're going to throw in all the, what are we going to put in there? All the numbers that come before the clustering terms and the numbers that come after that. So that we can just look at this set by inspection, say, hey, that is our supremum, which is another word for LUB, least upper bound. All right, so I'm going to throw in A1. And A2, comma, I'll also throw this in because there could be negative numbers. So it doesn't matter. As long as, so let's say this sequence started with negative numbers. Let's say there was a A7 was here. This negative number, if I took a term from the left side of 0, it will be a negative number. And if I put it in here, we will reorder the terms. Because the negative terms with absolute value numbers might be bigger than the original positive terms of the sequence. So this arrangement, this order that we are putting in has to work with that as well, okay? So we have 3 here. We can skip 4. And we put the last one, A4 is the last one, so let's just throw it in. And then we skip all of these and we put this one here. So which is the supremum? This is a set that contains its least upper bound, right? Here's an example of a set that contains its least upper bound. Does it contain its least upper bound? Box. This is an upper bound. This is an upper bound. It is contained in it because we got the square brackets. Now, does it contain its least upper bound? No. So this is a situation where the least upper bound is inside. There are obviously numbers bigger than m. There could be an m2 and m3 right here. So, and so all we have to do is to figure out what the supreme, what did we have to do here to figure out what the supremum was? Look at the right endpoint and the value of the right endpoint. What do we do here? We look for the largest element. It's called the maximum of the set. That is our supremum. So therefore, m equals 1 plus. All right. Once you've got that, then we can say now I was having more fun yesterday on Wednesday. Kind of sad about this. Okay, then it follows, book says, follows that we can say what? We can say what? So it says, and then it follows and it writes, what is the step now? So we have figured out what the m is, and we go back to this. This was our last step, and we replace the thing in the box with m. That's what happens at this stage. So we go back to this thing. So I'm going to write this thing here. It follows that an is less than 1 plus, and then it follows that this thing is actually equal to So if you look at the PowerPoint slides, it says, then it follows that an in absolute value is less than or equal to, I do this here, which is slightly confusing, but not really. Because what we're doing is, we can't, in a sense, we have replaced that, but what we're really doing is this thing here. We're not really directly doing algebra to this. That's just it for me. Is that right, Ryan? Because we have to bring in the equality, because that's the definition of a upper bound. But in fact, we do, this has to happen because this value is less than 1. So yeah, it doesn't really matter. Yeah. So there's this, okay, very good. It doesn't really matter. So even if it's always false, it will still hold. Okay. Which is in fact true in this case by our picture, that this m is bigger than and is not equal to any of the terms of the sequence. Now the fun part happens. And actually, shit, I erased that. So we're done with the proof. I just want to draw the picture again quickly. So we had this picture, which I shouldn't have erased. This is the worst way to teach math using just one whiteboard. But let's say here's our picture quickly. And then here is our clusters of A, all right. And then we have the A here, A minus epsilon 1, A plus 1. That's our epsilon. It could have been half, it would have worked. And this is our upper bound. Okay. And what did we show at the very end? We were able to show this thing here. That whatever A, we were able to show this, right? If this is M, and this means all terms of the sequence is between M and minus M. Therefore, anybody, what should I write here? Minus or what is the value of M? There you go. Well, just to remind us that that is the actual numerical value of the letter M. If we found where it sits, we take the negative and we find the exact spot, stick that in, and now we can see that the sequence is inside this closed set, right? This is a closed set. Let me give you a closed set here. 1 plus this is a closed set. Is that true? What's the left end point of the closed set? Minus M. What's the right end point of this closed set? Positive M. And now we can see that here. So in other words, so when we did the proof, we found the upper bound, and the upper bound allowed us to get the lower bound. And the idea is that a convergent sequence always fits into between a closed set like this, or minus M. Okay. And that is the situation here. So we have a convergent sequence here. This is where it converges. It converges around A. And then the upper bound turns out to be, so we've calculated a number that sits to the right of this open interval here, A minus 1, comma, A plus 1. Now what we have to do is we have to verify if this is the upper bound or not. In other words, we have to verify whether this number here is larger than any term in the sequence. And in order to do that, and the notion of something having an upper bound means we're dealing with sets. So we have to think of the sequence as a set. And what we do is, and we want to just inspect the set and figure out if this is the upper bound for that set or not. And if you have a finite set's maximum element is the same as its supremum or LUV, least upper bound. So we are now, by using, and right before this, we use the triangle inequality property. to find this number. And we found that it was right here. It is one more than the limit A. Okay, so we use that. So we got this number through the triangle inequality. Now we need to verify whether this number is a upper bound for that. Okay, and so let's do that. And so we're going to use the sub. So upper bound, of course, we're calling it M equals the sub using this, the least upper bound. We're applying this function sub to the set here. And the set, we're going to throw in all our terms in here, the finite terms. We're going to pick the finite terms from this picture and put it in here. And also, and I talked about that earlier, where if A1 was a negative number, if I put absolute value number here, it might end up becoming a bigger number than this one. So we will have to reorder the set. But we are only putting the if this is our last number from the left-hand side, n would be 4. Right? That's the threshold. After A sub uppercase n, all the elements of the sequence fall within one distance, because this is our epsilon of A. Okay, so comma, and in fact, let's put this here, A n minus 1 dot dot A n minus 1. So this is the last term before all the terms end up in this open interval, and they don't fall anywhere else to infinity. There'll be infinite terms here. And then we find this guy on the right-hand side of our open interval right here. So we picked up all of the numbers outside of the open interval. Now we got a set. And if you have a finite set, like this, then its maximum is also its supremum. So supremum. So just by inspection, you go all the way to the right, and that's your supremum. So M gets this value. And again, why did we have to bring in the sets? Because the idea of upper bounds, lower bounds, supremum, infimum have to do with sets.